Hi, this is Ryan Long. This is my final physics video, and I'm going to be talking about the scattering of light and Huygens principle. The scattering of light is the process of light absorbing into a substance, then re-radiating out in a variety of directions or all directions. Scattering of light plays a very important role in our lives because almost all objects scatter light. The scattering of light is the reason why the sky is blue, sunsets are red, and explains many other phenomena that exist in our world today. Huygens' principle is a method for knowing the shape of a wavefront at some instance, the shape of the wavefront at a later time. The principle assumes that every point of a wavefront may be considered the source of secondary wavelets that spread out in all directions with a speed equal to the propagation of the wave. So we're going to assume the propagation of the wave to be v, and we want to know where the wave will be at some time t later. So the wavelets, which extend out from the original wave, which will be right here. So the original ray of light radiating outward, and the wavelets created here, with the radius being the velocity times t. So when we draw the tangents to the wavelets and connecting all of them, we will now have the new wavefront of the wave that propagated out at a time t from the original moment. Huygens' principle is important because using the principle we can derive the laws of reflection and the laws of refraction. When looking at the bottom left example, these lines that the cursor is highlighting show the propagation of the wave, where the light in the top right section is propagating downward and not being affected by the surface because it hasn't reached the surface yet, where this bottom left, the light rays can't come down and already hit the surface. So we can continue to draw the wavelets right here, which are below the surface. If it went through the surface, this is where the wave would have propagated. But because of the surface, so if we take this point here next to M, we would still have drawn the radius vt of the circle of the wavelet. But since it hit the surface, it is not going into the surface anymore. It is reflecting off the surface. So if we look over at the diagram on the right, which is a zoomed up version of the shaded triangle here, we can see that the radius of the wavelet is vt, and we're drawing it at the point of contact with the surface. So the wavelet originally comes in from the top left and heading towards the bottom right, and hits the surface and reflects back up. And using these two angles, we show that the angle of incident is equal to the angle of reflection. For showing how Huygens' principle gives us the law of refraction, we have two materials. We have material Na and we have material Nb. And these lines that my cursor are highlighting is the wave propagating through material A into material B. And the top is just a zoomed out version of the bottom diagram. So let's look at the bottom diagram. So this wave is propagating to the top right corner, and here at this point the light is hitting the surface between the two materials. So when traveling in material A, it's going to have a uniform velocity, but since the index of refraction for the material B is greater than that of the material A, once the light hits the surface with B and starts traveling into the material B, the velocity is going to change. The original velocity is VA, and the second velocity is going to be VB, where VB is less than VA. So in the instance between contact and on the same light wave, so the contact here and up here, farther up on the ray, to this point farther into the material, back where this section of the light hits the surface, is the same amount of time. But because the light ray in material B is traveling slower than material A, the distance here is less than up there, and so the angle of A is going to be a bit larger than the angle B, the angle of refraction. Now to talk about the scattering of light, I'm going to use the example of a cloud. Now I'm going to talk about why clouds are white, because everyone can agree that clouds are in fact white. So we have clouds, which are made up of tiny ice crystals. So there's millions of ice crystals in the clouds, and sunlight traveling from the left comes into the cloud, and the light rays will start hitting these ice crystals, and when they hit the ice crystals, they're going to start refracting in all directions, and they're going to continue to hit other ice crystals as they refract from ice crystal to ice crystal. So we're going to have all these different wavelengths of light reflecting from ice crystal to ice crystal, and refracting and reflecting, and a lot of these light rays are going to reflect up into space and not to Earth, but some of the some of the light rays are going to reflect down to Earth where people can see it. And since there's so much refraction and reflection going on inside the cloud between all the ice crystals, we're gonna get a plethora. We're gonna get all the visible wavelengths of the visible spectrum, and because the viewer is getting all the visible light rays, wavelengths, then that's going to turn into the color of white. My worked example is from the book number 28 from chapter 33. The main reason why I picked this example is because it happens to be the only example in the book concerning the scattering of light. The problem reads, let me get to it. The problem reads, a beam of white light passes through a uniform thickness of air. If the intensity of the scattered light in the middle of the green part of the visible spectrum is I, find the intensity in terms of I of the scattered light in the middle of the red part of the spectrum and in the middle of the violet part of the spectrum. So we know that the shorter the wavelength, the more the light is refracted, and the intensity is inversely proportional to the fourth power of the wavelength lambda. So intensity equals some constant over lambda to the fourth power. So the wavelength for green is 520 nanometers. The wavelength for red is 665 nanometers, and the wavelength for violet is 420 nanometers. So we need to take, in order to do this problem, we need to take the ratio of the intensities of red to green. So basically, we have I red over I, and we plug in it. We have K, and then it turns into K over lambda's the fourth red over K divided by lambda fourth green. We do all this blah blah blah, and it turns into 520 nanometers over 665 nanometers raised to the fourth. This value is 0.374. So the intensity for the red in terms of I is 0.374 I. And now we need to do the same thing for violet. And when we do all this blah blah blah, it turns into 520 nanometers over 420 nanometers raised to the fourth, which is 1.35. So the intensity of violet in terms of I is 2.35 I. And that concludes my discussion of the scattering of light and Huygens principle.